Okay, here we go. Getting into the introduction to acid-base reactions, Bronsted-Lowry acids and bases. So there's a couple different types of acid-base definitions. There's what's called Arrhenius, which we don't focus much too on, but you probably saw in the book and we saw back in the day with honors chem. And then Lewis. Lewis acids and bases are not covered on the AP exam, so I will not be going into them. Try to just minimize what we got. So an acid's a proton donor. You should understand a proton to be an H plus ion. And a base is a proton acceptor. Therefore, acid-base reaction, it's transferred from acid to base. Think of it almost like we think of ionic reactions transferring an electron. So you'll often be given a chemical equation. HCl is the acid because it's donating the hydrogen. It's the one that's giving it. H2O is the base in this case. H3O is the conjugate acid. Cl is the conjugate base. So these come up with acid-base pairs. So the original acid and the conjugate base. The original base and the conjugate acid. This is how we're going to pair them up, okay? And essentially, you can see it's kind of a before and after. Before, hey, had a hydrogen. After, where'd it go? Hey, I was missing one. Hey, now I got one. So keep in mind that these pairs are going to be extremely important. There'll be a whole section of acids and bases, but for right now, we're just getting the idea of these concepts down just to start. Well, it seems like I got ahead of myself because that's what this whole slide says, essentially. So conjugate acid is the species form when the proton's added to the base. Now that it has an extra hydrogen, it's an acid. Conjugate is just this term that relates to the base before, kind of like actually, I'm not sure what conjugate is as far as in an English sense. It's a one to Google if you so care to. Conjugate base is going to go with the acid, okay? So the acid base is always going to be in a pair, either with the conjugate acid with the base or the conjugate base with the original acid. And keep in mind, when we say acid base, we're talking about the left side. Conjugates are going to be on the right side. And the acid-base pair are the two substances, kind of the before and after for each component. So there's two conjugate acid-base pairs for each of these reactions. So as an example, identifying the acid, the base, and the conjugates. So the acids and bases are going to be on the left side, okay? Conjugates will be on the right side. Now, you see that there's this double arrow. That means it can go either way. Now, that also means that if we could call this side the acids and bases, and these could be the conjugates. Generally, that's not the way we describe it, unless you're talking about the reverse reaction, and the reverse reaction would be the reverse of the forward reaction. However, looking at this, we can conclude that water gained a hydrogen. So if it gained a hydrogen, it must have been the base. We can see this one lost the hydrogen, therefore it must have been the acid. Now, if I've already identified this as the base, and this is like what I'm looking at in order to determine, hey, did it gain or lose? That means this must be the conjugate opposite. This is the base, the conjugate acid, opposite of a base. Likewise, I see this one is the acid, therefore this must be the conjugate base. Get used to using these terms, get used to reading these terms because they're going to come up quite a bit on our tests. Now, water is the classic example of something called amphoteric. So water ionizes itself. The idea is that the two water molecules would collide together and transfer a hydrogen. Why would this occur? Well, considering the shape of water, to where the tip of my fingers would be the oxygen and my fists would be hydrogens, there's a whole bunch of space on this upper area for the oxygen. So a water coming in with a hydrogen coming down could get close enough in order to kind of be attracted and being pulled away from the other oxygen. This occurs to a very small extent. I believe the molarity at room temperature is 1 × 10⁻⁷ molarity. So it's a little bit smaller than a millionth of a molarity. So super small, but it does occur. However, that means it can act as an acid and a base. And if something can be an acid or a base in different situations, it can be called amphoteric. So an example here is the aqueous solution H2SO4. Okay. In this reaction, water's accepted the proton. We got this form. So acid, conjugate base, base, conjugate acid. Okay. Not too much of a stretch. However, this HSO4 could also become SO4 2-. So in this case, it's an acid because it donates a proton, and this is now a base because it accepts it. Again, you get these acid-base pairs, and H2SO4, so this could be going the other way and now become a base itself. Generally, it's when you think of you have more than one hydrogens available. So H2SO4 can donate two, so it's called diprotic. Phosphoric acid, H3PO4, is triprotic acid. Monoprotic acid, I guess technically exists and works, but most people just don't determine it that. We just call it an acid. So keep in mind that you will come across these in much later areas, but the idea is that the amphoteric just means it can gain hydrogens or lose hydrogens to become something new. It's not that big of a difference. I wasn't liking the way that previous page was looking. So when it talks about strengths and particles, like what this would look like, some things that are called strong. Strong means that all of it, or nearly all of it, will become dissociated in water, separate. So these are your strong acids. You see them in the textbook. Weak acids or bases will become unlikely to dissociate, so they'll be undissociated. You can see you get a little bit, but most of it will be not separated. Those will just be sitting around in the water. So something that is strong is a good conductor of electricity. Something that is weak is a weak conductor of electricity because you have very few ions. So you see how all of these are combined together in HCl. These are water molecules. You can see that there's a lot of transfer going on, a lot of ions in solution. HF in this representation, a lot of them are still HF when they're mixed with water. This is also true. You might be given an option which one of these is the strong acid or the weak acid. You can see that a lot of the acid, HA in a general sense, has been dissociated. A lot of conjugate base ions present, and a lot of conjugate acid ions present. Unlike here, where you only have one, this one would be in the middle of three. So we talk about relative strengths of particles, a bit being strong or weak, but when we look at particles, more ions present is going to be strong, less ions present is going to be weak, seeing more of the molecules. Now, we also have relative strength. It's a little bit different than we're going to go into more depth later in the year, but this is just the introduction to it. So this will be based upon evidence, and now only with water. So we have the ideas of acids and bases and conjugate acids and bases, but what it might dictate is that if you put one molarity of acetic acid in, and let's say another molarity of sulfuric acid in water, the same molarity, and you get more acetate ions than sulfate ions, what does that mean? So that would mean the idea if you get more ions, that had to have been a stronger acid than if you get less ions. So you need to look at the evidence, and this is only when compared with water. Second semester, we'll be able to use rules to determine strength between acids and bases, and they take a lot deeper idea of dealing with electronegativities and pulls like that, to where you can predict them on paper without having to react them with water and have evidence. So for right now, you'll be looking at it, be given evidence to those contrary ideas so you can determine, remember, if something is, can I go back? Nope. There we go. If something is strong, you're going to have more ions in solution, right? So in this case, you might have the concept of given another information, given more information, you can determine, hey, there's more acetate ions than sulfate ions. That must mean this one was a stronger acid because there's more of it. Those are the kind of concepts that you come across. Let me know what kind of questions you have, and I'll catch you up on the flip side.